The next speaker is Shani Ben David. She will talk about Hamming-weight proofs of proximity with one-sided error.
Thank you for the introduction. I'm going to talk about Hamming-weight proof of proximity with one-sided error. This is a joint work with Gal Arnon and Alon Rosen. So we start with an example. In 2022, Elon Musk initiated the process of acquiring Twitter. However, later on, he withdrew his offer, arguing that a large portion of Twitter users are spam bots. This sparked a major dispute. Twitter was arguing that this was a false claim and even tried to force Musk into the deal. Now, in order to solve the dispute, Musk wanted to verify that roughly 95% of Twitter users are real. We represent the users as a bit vector, where 1 indicates a real user and 0 a spam bot user. Back then, Twitter had 350 million users, so the vector V is huge. Naively, Musk could count the number of real users, but this is too costly, potentially requiring expensive individual checks, maybe even hiring a private investigator to check that a user is real. And this, for such a massive data set, this is impractical. Musk could check only a small number of users, nothing more than that. So this problem comes down to designing a proof system in which Twitter can prove to Musk that roughly or approximately 0.95 of the Hamming weight of the vector, 0.95, and allowing Musk to verify the proof by querying only a small number of bits, by verifying only a small number of users. So let's see what are the properties that we want from such a proof system. So first, we want framing-free proof system. We want perfect completeness. Let's say that we do have a proof system for the Hamming-weight problem, and we have two-sided error, even exponentially small error. In this case, even if Twitter was honest, Musk could deliberately choose randomness that will make this proof fail. Now, going with this as evidence to court might unjustly frame Twitter. So we want perfect completeness in which honest party cannot be falsely accused. We want Twitter to be willing to post the proof. Okay, let's move on to the definition. So we talk about Hamming-weight proof of proximity. We define Ham alpha to be the language of all bit vectors in which the Hamming weight of the vector is at least alpha, where we define a Hamming weight of a vector to be alpha if alpha fraction of its element has the value 1. Now in this setting, we talk about the vector V as huge and very expensive to query. So we have a prover and a verifier. The prover and verifier interact, and the verifier queries only a small number of bits from the input and then decides whether to accept or reject. Now, the two properties that we want is 1, perfect completeness. If the vector is in the language, then the verifier will always accept. And we want, now this was the framing-free property that we talked about. And soundness, we want that if the vector has the Hamming weight alpha minus delta, which means that the vector is delta far from the language, then the probability that the verifier accepts is bounded by some epsilon. This was a general definition, and let's see what are the models that we studied. So in this work, we'll perform a systematic study of Hamming weight proof of proximity with practically efficient prover, which means that in any of our constructions, the prover is very efficient. In each of the models, the verifier reads only a small number of bits from the input. So in the IOP model, the prover and verifier interact, but the verifier is restricted to read a small number of bits from the prover messages. In the PCP model, there is no interaction. The prover just sends a proof. And again, the verifier, using its own randomness, decides which bits to read from the proof, and it reads only a small number of bits. And for the MA protocol, the prover sends a proof, sends a message to the verifier reads the entire message, and decide whether to accept or reject. So in each one of the models, we provide an upper bound and lower bound, and let's see our results. So in the MA model, we provide proximity protocol where the verifier reads log n bits from the input, and the proof length is log squared n. Compared to previous work, this is an improvement of log n factor. Now for the lower bound, we provide lower bound for interactive proof with any number of rounds. So we say that any perfectly complete IP of proximity for the Hamming weight protocol has proof length that is at least log n minus log QV, where QV is the number of queries to the input. Putting parameters into this bound, we get the following corollary. So for a protocol where the verifier reads square root n bits from the input, the proof length must be log n. So even if we add interaction, even if the verifier makes many queries to the input, the proof length still has to be log n. So this means that our MA results is optimal in the proof length up to the log n factor. Okay. Moving on to the PCP model, we give a proximity proof where the verifier makes log n queries to the input. The proof length is sublinear, and the verifier reads log n times log n bits from the proof. Focusing on the input query complexity, this is a logarithmic improvement compared to our MA results. And we ask the question, what if we want to optimize the input query complexity? So what if we want to have just a single input query? In this case, we define SIQ PCP to be PCP with a single input query. So the verifier reads only one bit from the input. And we give a construction where the proof length is linear in the input side, and the verifier reads log squared n bits from the proof. To complete our study of SIQ PCP, we show that the linear proof length is actually inherent. So for the lower bound, we show that for a large range of alphas, every perfectly complete SIQ PCP of proximity for the Hamming weight problem must have a proof length that is linear in the input size. So if we want to optimize the proof length, we must have proof size that is proportional to the input size. Now we're going to see the power of interaction. So up until here, we saw an MA model and PCP model, which are non-interactive. Now we're going to move on to the IOP. So we provide a two-round proximity protocol with a single input query, and the proof length is log squared n, and the verifier is log n bits from the prover messages. So you can see that if we have just two rounds, you can get a single input query, and the communication complexity is still very good. Compared to previous work, Goldreich, Gur, and Rothblum constructed an IP protocol with log n rounds, single input query, and the communication complexity was polylog n. As a lower bound, we show that any semi-adaptive, perfectly complete IOP of proximity for the Hamming weight protocol has the following condition, where semi-adaptive IOP is an IOP that is stronger than non-adaptive but weaker than adaptive, so it lies somewhere in between those two models. And putting parameters into this bound, we get that if the communication complexity is polylog n, and the verifier reads square root n bits from the input, then the verifier still needs to read just below log n bits from the prover messages. Okay, so our result has an additional application. We show a transformation. We show that Hamming weight proof of proximity protocols can actually be used to transform PCP with imperfect completeness into PCP with perfect completeness, and IOP with imperfect completeness to IOP with perfect completeness. And in this transformation, we maintain roughly the same query complexity and proof length of the protocol, and the better parameters that we get in our Hamming construction, the better parameters we achieve in the transformation. Okay, up until here, this was our results. Now let's see a high-level description of our PCP construction. So here we focus on two main things. One, minimizing input query, and we want to still maintain sublinear proof lengths. Okay, so we define good shifts a la Lautman, but not exactly the same. So we have Z1 to ZT, and we say that Z1 to ZT are good shifts for specific vector V, if for any row, V row has high Hamming weight. And let's see how we define V row. So we have Z1 to ZT, we have the vector V, and V row is a T-bit vector, where the ith element in V row equals to the element in V in location rhox or Zi, sorry. So the ith element in V row is defined by Zi. Good, so we have n such shifted vectors. Moving on, we show that for small t, so small number of shifts, specifically we show for theta log n, we get two properties. We get completeness and we get soundness, where completeness means that if the Hamming weight of the vector is at least alpha, then most shifts are good, which means that for any row, the Hamming weight of the vector V row is high. For soundness, we say that if the Hamming weight of the vector V is alpha minus delta, then for every shift that we choose, the probability is that V row will have high Hamming weight is bounded by some epsilon. Now these two properties naturally leads to a construction. So we get the prover send good shift, Z1 to ZT, and then the verifier will sample row and check that V row has high Hamming weight. Now this construction will have both completeness and soundness. The problem here is that in order to check the Hamming weight of V row, the verifier needs to read many bits from the input vector. In order to solve this, we kind of do a recursive step and make the prover prove for the small vector V row, that the small vector V row has high Hamming rate, rather than the large vector V. And the verifier will sample row and check that the proof that V row has high Hamming weight. Now this will have low query complexity, but the problem is that there is no interaction here. The prover doesn't know which V row the verifier is going to choose. So it has to send, it must send a proof for each V row. So the proof length is going to be linear in n, so in the input size, which is too large, and we fail to maintain now the second goal. So how do we solve that? Our last step is to divide those, I need to wrap up. So essentially we just prove for large groups. This works, but there is a challenge in the soundness, and that's it. Thank you all.